In 2004, a discovery was made regarding the computational complexity of a game called Lemmings. This discovery meant that if anyone could find a faster way to solve this puzzle game from 1991, it would help cure cancer, be a huge financial security risk, and give an answer to the biggest open question in all of computer science instantaneously. The first question we're going to think about is, what is the relationship between filling up a bag with the most valuable items possible and the game of Lemmings? Well, in terms of computational complexity, they are more similar than you would first imagine. Now, this leads us to a few more questions on how any of this makes any sense. Well, first, when solving a problem, we're going to need an algorithm. So, what makes one valid algorithm better than another? How can we measure the effectiveness of an algorithm, and what factors do we need to consider when determining the effectiveness? Well, in computer science theory, an algorithm X can be considered better or more efficient than another algorithm Y if it has a better asymptotic running time than Y. Asymptotic running time represents how many elementary operations are performed with respect to the input dataset of size n for a very, very large number n. To give you an idea of what this might look like, here we have a string of length 10, 20 and n for a very large number n. Another commonly used data type in computer science is an array. We reference the elements of the array via the index, which starts at 0. Having seen an array of size 20, an arbitrarily large array of size n would look something like this. When evaluating the asymptotic running time of an algorithm, we only really consider the worst case performance of the algorithm given an input. For example, if you wanted to determine how good an algorithm was at sorting, it wouldn't be very enlightening if the input that you were given to be sorted was already sorted. This would be the best case scenario for this algorithm. So instead, we determine the asymptotic running time of an algorithm based on its worst case input. As we defined earlier, asymptotic running time is determined by how many elementary operations an algorithm takes in order to process the input to the algorithm and output appropriately. An elementary operation is normally a basic read-write operation, such as an access to an array. We can represent asymptotic running time using big O notation. Big O describes a functional relationship between the input size of an algorithm and its respective asymptotic running time. Here we can see the different categories of time complexities, from fastest to slowest. For all of these time complexities, we are considering the upper bound of the running time of an algorithm. For example, constant time algorithms have their running times upper bounded by a constant number that doesn't change regardless of input size. However, constant time algorithms can have their running times influenced by variables, although the effect of those variables must be upper bounded by a constant number. If a problem is found to have a faster algorithm than before, but it is in the same time complexity category, it is seen as an achievement, but it would generally be much more of a breakthrough if the newer algorithm was in a faster category. We're considering these rates of growth when evaluating running times for these algorithms. Often we want to use computers to process data from a very, very large data set for whatever means. So, if we have an algorithm that does not scale well for larger inputs, then it won't be as useful in these situations. Now, since we're thinking about asymptotic running times in relation to the category they're in, we can draw some equivalences as follows. Two functions under big O notation are said to be equivalent if both of their largest asymptotic time elements are in the same time complexity category. So, in our first example, we have big O of 900,000. Since 900,000 is a constant, we can just say that under big O notation, this function is equivalent to big O of 1, constant time. For our next example, we can see that the element in the highest time complexity category is 777n. We can see that this function is linear and is therefore equivalent to any other linear relation such as 6000n. These can all be categorized as big O of n, which will give us the time complexity of linear time. The same intuition holds for the polynomial example, where we are selecting the element of largest time complexity, which is n squared over 2, which is the same as any other polynomial relationship, which can all be categorized as polynomial time. Finally, an example for exponential running time, we can see that this element is exponential and has the highest rate of growth out of the other elements in that function. Therefore, it is equivalent to any other function which has the exponential element as its slowest growth rate. Here is a non-example that shows us two functions under big O notation that are not equivalent. This is because their elements of highest growth rates are in different time complexity categories. Using this knowledge, let's have a look at a few different algorithms and evaluate their running times. For our first algorithm, we want to find the first constant k elements of an array. K can be equal to any positive integer and doesn't depend on other variables such as n. K can be 1000, 2000, 1, 4, it doesn't matter because it won't have any effect on the overall asymptotic running time of the algorithm. A simple algorithm for this problem will be to iterate through the first k elements of the array and output each one. So for example, if we only had an array of size 10 and we're given that k equals 4, we just need to output the first 4 elements of that array. Now, for an array of size 20, let's say we're given k equals 1. We only have to output the first element of this array, and we're done. However, in the general case, don't forget that we're dealing with not 10 or 20, but a very large variable integer n. So for our general case, we can have k equal to any constant positive integer that we like. For k equal to 1, we only have to compute one elementary operation to calculate our answer. Therefore, the running time of this procedure for k equals 1 is upper bounded by the integer 1. For k equals to 333, we have to access the array 333 times, which will take 333 elementary operations. So the running time for this value of k will be upper bounded by 333, meaning we will have a constant time algorithm. This same logic applies to any size of k, but for a general value of k we'll have to perform k lookups and k elementary operations, which will give an upper bound for the running time of this algorithm of a constant positive integer k. Hence, we're left with a constant asymptotic running time. To get a better understanding of why we're using upper bounds, let's have a look at this algorithm. This time we're finding the elements of an array from index 0 to n mod k, quite similar to our last problem. However, this time the number of elements that we're trying to find depends on the variable n. Therefore, the number of elementary operations for each k will vary based on the size of n. So what does the operation mod mean? Mod is the shortened form of the word modulus, which describes the operation of finding the remainder after dividing two numbers. For example, 9 mod 4 is 1 because we're left with the remainder 1 after division. 103 mod 5 is 3 because we're left with a remainder of 3. And this number mod 5 is equal to 0 because it's divisible by 5. Now let's see an example of how this algorithm will run for k equals 3. Well, when n is a multiple of 3, we know that the result of n mod k will be 0 because n is divisible by 3. However, if n is 1 more than a multiple of 3, then we know that n mod k will be equal to 1 because we'll be left with 1 remainder. Now, since we've covered the case of if n is a multiple of 3 and if it's 1 more than a multiple of 3, the only other possible case we can have is if n is 2 larger than a multiple of 3. Since if n is 3 larger than a multiple of 3, n will then be divisible by 3, so we'll have an equivalent situation to our first case. And of course this cyclic pattern continues for all values of n. Therefore, for k equals 3, we're accessing at most 3 elements of the array for any number n, giving us the upper bound of a constant number 3, thus resulting in a constant running time. So hopefully you can see that for whatever value of k that we choose, the maximum number of elements in the array we'll have to access will be k, meaning that this whole algorithm is upper bounded by the constant k. Therefore, we have achieved a constant running time. Now, to further build intuition on how we evaluate these algorithms, let's have a look at a linear time algorithm. So here we have a problem where we need to find the largest integer in our array. Since we can only access each element one by one, if we don't access every single element, then we have no way of knowing if we've found the largest integer in the array if we've left any elements unchecked. For example, if you're going to check through the array from left to right, the largest integer could lie all the way on the right hand side and you would be none the wiser. So, for an array of general size n, regardless of any other factors, we have to search through all n elements of the array before we can safely say we found the largest integer. Therefore, since this algorithm is upper bounded by n, we can say that this algorithm runs in linear time. For an example of a polynomial time algorithm, let's have a look at a sorting algorithm. If you don't know what a sorting algorithm is, it is a procedure that, given any array of numbers, will be able to sort the array from the element containing the smallest number to the element containing the highest. There are many different sorting algorithms out there, some with different purposes than others, and many that have objectively better running times than others. In this example, we'll have a look at a very simple sorting algorithm called bubble sort, which we work through the array left to right, and if the number in the current index is larger than the number in the next index, the algorithm will swap those two numbers. Therefore, if the largest number in the array is at the front of the array, it will get swapped with every single other element in the array until it bubbles up to the top of the array. This procedure is carried out until no more swaps are required, thus leaving us with a sorted array. Intuitively, the worst case running time for this algorithm will be a situation when we have to bubble up as many numbers as possible. So if we're given an array in reverse order, this will give us that worst case scenario since we have to bubble up every single number before we can say our array has been sorted. So in this worst case situation, how many elementary operations do we need to carry out? Well, for an array of size n, we will need to iterate over the array n plus n minus 1 plus n minus 2 sequentially until we're left with our last element. This sum of numbers is equivalent to saying we're summing all numbers from k equals 1 to n. We can evaluate this sum quite nicely to n squared over 2 plus n over 2. Don't worry if you don't understand how we evaluate that, it isn't important to what we're trying to show. All that we've shown is that we need to perform n squared over 2 plus n over 2 elementary operations in the worst case. Therefore, under big O notation, we get the equivalence of O n squared, and therefore we now know that bubble sort is a polynomial time algorithm. Now we almost have everything we need to be able to understand a very important problem in computer science. All that's left is to give you an example of what an exponential time algorithm looks like. This brings us to the subset sum problem, where given an array of integers where no integer is repeated, calculate whether or not any subsets of the array can sum to a target number k, where k is a positive integer. A set is essentially an array of numbers such that there are no repeated elements. So for example, we can't have more than one element containing the number 20. Here's an example of how this problem will work on a set of size 3. First, we need to find all the subsets of the given set and determine if any subset exists such that the sum of all numbers in the subset equals our target number. We will need to process all subsets of the given set because in the worst case, none of them will sum to make the target number. A way in which we can find all subsets of a set and calculate their sum is by processing subsets in a way that creates a tree, where for each element in the set there is a branch where we include said element and another branch where we exclude it. As you can see, this will enumerate all subsets of our set. Now we're ready to consider the general case of a set of size n, and we will demonstrate why this algorithm takes exponential time. Here we can see the general idea of what the tree will look like for this example. By taking all the top branches, we include absolutely every element in our set, and by taking all the bottom branches from our first element, we are left with the empty subset. And as you can see, every single other subset possible will be enumerated using this method. Now all we have to do is for each subset, check if the sum of all numbers in the subset equal our target number. If it does, return true. If it doesn't, keep searching until there are no more subsets left to verify. As we can see from the diagram, as we add more elements, we will have to process exponentially more branches. When we process a yes branch, we need to perform an array access. Therefore, every time we include a yes branch, we have to perform an elementary operation. And as you can see, for n elements, we require 2 to the n operations, giving us the exponential running time. Now finally, we're only a few steps away from answering all the questions I've asked in this video. However, for this next problem, there will be a question I will not be able to answer, and we'll see why in a second. Let's introduce P versus NP. P and NP are two complexity classes which contain a variety of different decision problems. A decision problem is a problem with a yes or no answer, like the subset sum problem, since in that problem we were asking, can this target number be achieved via the sum of any subsets of this set? The complexity class P contains all decision problems that can be evaluated in polynomial time. Examples of these problems in P are problems such as multiplication and sorting algorithms such as bubble sort, which we saw earlier. However, we would have to adapt bubble sort slightly to be in the form of a decision problem. And as far as we're concerned for this video, the NP complexity class contains problems that can be certified in polynomial time. In order to determine if a problem is a member of NP, we need a certifier. Given a decision problem and a polynomial length solution, the algorithm for the certifier should be able to determine if the given solution is valid or not. The certifier should be able to determine between all correct and incorrect solutions to the problem. Now is a good time to note that for a problem to be a member of NP, the problem in question must have a finite number of solutions. Let's see how a certifier algorithm would work for our subset sum example. A solution for our subset sum algorithm will be given as a subset. The certifier must determine if that subset is in the original set and if all elements in the subset sum to the target number. For this example, it's quite easy to see how this can be done in polynomial time. Therefore, the subset sum problem is a member of NP. An example of other problems in NP are problems such as integer factorization, Sudoku, and all problems in P. Since we know that all problems in P can be evaluated in polynomial time, they can therefore all be certified in polynomial time, which is the reason why all problems in P are in NP. Sometimes problems that were previously exclusively in NP have polynomial algorithms discovered for them, which lands them in the P complexity class as well. And the big question is, do all problems in NP have polynomial time algorithms? P versus NP is the most famous, most significant, unsolved open question in all of computer science theory right now. This question is quite literally a $1 million question, since it is in the set of millennium problems who offer a $1 million cash prize to whoever answers this question and many other questions posed in the turn of the millennium in 2000. Another complexity class we need to consider for this video is the NP-Hard class. A problem X is NP-hard if every problem Y in NP can be reduced in polynomial time to the problem X. The name of the class NP-hard is derived from the fact that the set of problems in the class are thought to be more tricky to compute than problems in NP. However, from our definition of an NP-hard problem, if a polynomial time algorithm is found for any problem in NP-hard, then since every problem Y in NP can be reduced in polynomial time to that problem, then that problem's solution can be used to solve Y and all problems in NP in polynomial time. If this ever does happen, this will immediately imply that P equals NP. Some problems that are in NP-hard are the halting problem, Sudoku for an n by n sized grid, and the subset sum problem. The final complexity class we need to consider is the NP-Complete class. Quite simply, a decision problem is called NP-Complete if it is a member of both NP and the NP-Hard class. Example of problems in NP-Complete are again Sudoku and the subset sum, as well as many other problems, one being the Knapsack Problem. While P is not equal to NP, problems in NP are at least as hard as problems in P, problems in NP-Complete are at least as hard as problems in NP, and problems in NP-Hard are at least as hard as problems in NP-Complete. I've singled out the Knapsack problem, as particularly the 0-1 Knapsack problem may seem like a problem that at first glance isn't too tricky to solve. The problem is as follows. Given a set of items, each with a weight and value, determine which items to include in a collection so that the total weight of all items to be put in the knapsack is less than or equal to the given weight limit of the bag, whilst maximizing the total value of all items selected. It's called the 0-1 knapsack problem because you either include 0 or 1 of each item, whereas in the general form of this problem, there is no limit to the amount of each item you can include. Here we have 5 items we can choose to include or not include in our knapsack. Let's see what would happen if we were to include the cheese into our knapsack. Since the weight limit for the knapsack is 15 kilograms, if we include the bottle, we'll be at a total of 16 kg, thus exceeding the weight limit. Therefore, we cannot include the bottle. Now when deciding between these last 3 items, we want to maximize the value. So in order to do so, we're going to choose the chicken and the corn to achieve a total value of $10. Now let's start off by not including the cheese at all. If we do this, we can see that we can actually include all the items as we will not exceed the weight limit of 15 kilograms. Now, we have achieved a much better value than we had if we had included the cheese. Therefore, the maximum value achievable with all these items will be $15. Before we have a look at the algorithm for this problem, let's first have a look at the representation of this problem. For the input to this problem, we'll have the items and their value given in one array, with the index representing what the item number is. Unlike in all our previous examples, we're going to start our indexing at 1, just to make things easier to understand. This won't change anything about the actual algorithm. So we also have a second array containing the item's weights, again indexed by the item number. Our last input will be the integer weight limit of the knapsack, and the output of this problem will be the maximum value that can be achieved given all of these inputs. Now, here's a look at the algorithm for the knapsack problem and a demonstration with some example inputs. The first step of the algorithm is to define an n by w array called M. What we have now is an m by w 2D array which will represent a table which we use to decompose the knapsack problem. To initialize the table, we will fill the first row and the first column with zeros. Finally, we will be able to fill this table and solve this problem only needing to use n times w elementary operations. Now let's show what exactly is going on when we're filling the table. Firstly, here is our empty m by w 2D array or table. We initialize this table by filling the first row and the first column with zeros. This makes sense because if we have 0 items, it doesn't matter what the weight limit is, we're not going to include 0 items. And for the first column, no matter what item we choose, if the weight limit is 0, we won't be able to include any subset of items. We fill this table by solving the knapsack problem for smaller subsets and smaller weight limits, and then building upon that to include all items and all weight limits until we find our answer. So our first step is just to solve the problem for if we only had the first item with weight 1 and we had a weight limit of 1. Well, since we're within our weight limit, we can include this item to achieve the maximum value possible for this sub-problem. Now since we know that we can include the first item with a weight limit of 1, then if our weight limit increases to 2, we know that we can still include the item because the weight limit has only increased since 1. Therefore, we know the maximum value achievable for this sub-problem is 1. Now, the same logic applies for all weight limits greater than 1, so the algorithm will fill these spaces in the table in the same procedure as beforehand. Now, to keep building on our sub-problems, we're going to consider the subset of items including the first and second item. So again, we will fill out the table based on the different weight limits of the knapsack. If we have a weight limit of 1, since our second item has a weight of 2, this will exceed the weight limit. Therefore, we can have a look at our pre-calculated answer for 1, 1 to find our answer for 2, 1. Now when we consider these two items with a total weight limit of 2, we can now include the second item, as item 2's weight is now within the weight limit. Now we need to consider what option will maximize our value. If we include the item 2, then we'll need to subtract the weight of item 2 from the current weight limit, and add the value of our current item 2 to our previously calculated value for a subset of items 1 with a weight limit of 0. This will just leave us with a value of 6 plus 0. Or if we do not include item 2 and instead use our previous calculated optimal value for 1, 2. Well, since item 2 has a value of 6 and our first item only had a value of 1, it would of course be optimal to include item 2. Therefore, we can update the value of 2, 2 to our newfound optimal value of 6. Next, we're going to consider the weight limit of 3 for this subset of 2 items. Now we're going to see if it's better to use our pre-calculated value for 1, 3, or if it's better to add our new value for the item 2 to our value of 1, 1. This is again because we're subtracting the weight of our second item from our current weight limit of 3. Therefore, we're left with a weight limit of 1, and we only have the first item left in our subset. So, our second item's value of 6 plus 1, 1 will give us the optimum value for this subproblem of 7. This is of course equivalent to saying we're including both items. So as we go up the weight limits, we'll do the same comparisons as before, but since all the values from now on for the row of 1 only have the value 1, then for any higher weight limit than 3, the optimal value for this subset of 2 items will be 7. We can continue to rebuild the rest of this table for the rest of the subsets in the same fashion we've just shown. By building these smaller subproblems on top of each other, we can then find our final result for our full set of items and our full weight limit. Using this method, our final entry to the table will give us our desired optimal value given the inputs to this problem. Since we built this table in this way, it's actually possible to unpick what we've done to find all items included to find this maximum value. It is not required by the problem to identify which items are to be included in the knapsack to achieve this maximum value, but it is a nice visual result nonetheless. I mentioned before that the knapsack problem is a member of the NP-Complete class, but don't forget that in order for a problem to be in these complexity classes, they have to be asked in the form of a decision problem. So the decision version for this problem just requires us to add an extra input v and check if the optimal value for this knapsack exceeds or does not exceed our inputted value v. This simple additional constraint to our problem does not at all alter the computational complexity of our algorithm from before. But wait, at first glance, this problem seems like it can be solved in polynomial time, since we are only required to do n times w elementary operations. Well, something about the nature of our input w makes this not polynomial time, but pseudo-polynomial time. This is because the computer representation of the integer w does not scale nicely as the size of w increases. An integer is represented as binary in computation, so as integers get larger, the amount of bits required to express the given integer will also get larger. Let's have a look at a quick example to help us illustrate this point. Suppose we have 5 items with their respective weights and values, and we have a weight limit of 8. 8 is represented in binary as 1, 0, 0, 0. And since 4 bits are needed to represent this number, we can say that w has a bit length of 4. Now when we compute n times w when we're evaluating our asymptotic running time, we'll be left with a value of 40. Now suppose we double the amount of items that we have. In this case, we'll have 10 items with their respective weights and values. If our weight limit is unchanged from before, n times w gives us a result of 80. Now here's when we run into our problem. If we want to double the size of w, this doesn't mean that we double the value of w, it actually means we double the bit length of w. This means our doubled number won't have a bit length of 4, but a bit length of 8. And the denary equivalent of 1 followed by 7 zeros is 128. So when we double the size of w, we significantly increase the size of the denary value of w. When we now calculate n times w, we're left with a much bigger result of 640. So we can see that as the size of w and n increases, since w increases at an exponential rate, this leads to n times w also increasing at an exponential rate. We can instead imagine the runtime of the knapsack problem to be n times 2 to the power of the number of bits in w. There are other algorithms in NP-Complete that also have pseudo-polynomial time algorithms. For example, there exists a pseudo-polynomial time algorithm for the subset sum problem that we looked at earlier. However, the algorithm that we looked at was not pseudo-polynomial. These type of problems are classed as weak NP-Complete problems. So now we understand what the knapsack problem is and its algorithm. What exactly is its connection to the game Lemmings? In 1972, a computer scientist named Richard Karp would detail 21 computational problems in NP with polynomial time reductions from a problem called SAT. SAT, or SAT, is a problem based around Boolean satisfiability and has a very interesting relationship with the rest of these problems. So from this tree, we can see that 3SAT has a polynomial time reduction from SAT. And since these problems have polynomial time reductions from each other, a problem on the far right like maxcut can be reduced in polynomial time from a whole chain of problems before it, leading to the 3SAT problem being reduced from SAT. But since we're just linking many polynomial time reductions together, we can now simply say that there exists a polynomial time reduction from SAT to maxcut, since performing multiple polynomial time reductions still just takes polynomial time. On this list of 21 problems, Knapsack is listed as one of the 21. However, over time, many other problems have been added to this list once a polynomial time reduction has been found from one of these problems to the new problem. One such example of this is the problem of being able to solve the puzzle game Lemmings given a polynomial time limit. This and many other problems have been added to this tree over the years. So now we have finally found a relationship between Lemmings and the knapsack problem. But this isn't very satisfying. There's no direct link between them. This is where the Cook-Levin Theorem comes into play. This theorem states that every problem in NP reduces to SAT in polynomial time. This means that we know that SAT is not only a member of NP, but a member of NP-Hard. And remembering our definition from earlier in the video, this means that SAT has confirmed to be NP-Complete. Also, since we now know that all NP problems reduce to SAT, that means that all 21 problems and Lemmings that we saw in the tree previously not only have a polynomial time reduction from SAT, but to SAT as well. This immediately means that all these problems in the tree that we looked at are now NP-Complete, since they were already confirmed to be a member of NP, and now since we know that they reduce to and from the SAT problem, then every problem in NP reduces to these problems. Therefore, All of the problems are a member of NP-Hard and NP, thus making them NP-Complete. So finally, we have a direct relation between Lemmings and the knapsack problem. What this now means is if anyone finds a polynomial time algorithm for any problem in NP-Complete, they will immediately answer the P versus NP question. So, if you think you know a fast way to solve any of these problems, whether it be Lemmings, the knapsack problem, or Sudoku, or you think you have a way to disprove it, then you will 100% go down in history as making the biggest computational discovery of the millennium. Thank you for watching.